Oh, it's only you, Donna. Are you
Hey,
there?
I am here. I'm sorry, I was finally getting a call back from my dentist.
Is your
Having
appointment
whoa, I know.
is your appointment at 2:30?
No, no,
That's a joke. 2:30?
you're clever.
Yeah, yeah,
No,
yeah.
I'm calling them every 30 minutes, their emergency contact line, and nobody's calling me back. Finally, they call me back as soon as I finally put the phone down. I'm like, fine, I'll just deal with this after the meeting. And so,
Fair enough. Fair enough.
yeah,
Listen, I'm going to stop recording this so that this conversation doesn't end up on the other
I
thing.
appreciate that.
All right. So give me a second, and I'll restart recording. Okay. I might
Okay,
have to close the meeting and reopen it. So just give me
no
a
worries.
second. Sorry about that.
That's okay.
Actually, I will end. I'll end the meeting, but then well, no, I can't end it because then it won't restart. I'll just have to stop it.
It's okay. Don't worry about it.
Uh, no, it doesn't matter. I'll have to edit it out. All right, I'll do that. Hey, Rebecca. All right. So we've got two of you here. That's all right. I'm glad to have somebody here. I didn't want to be just talking to myself. That would have been pretty awful. All right. So what we're going to do is we're going to focus on. Oh, hang on. I need to share my screen. That would be really helpful so that you can see my screen. So I'm going to share my screen. Let's do it. All right. You can see my screen, I hope?
Yep.
Okay, good. Now we're focusing on two questions today. We'll focus on questions 6 and 7 on Tuesday. But today it's going to be questions 4 and 5 that we're going to be focusing on here. So question 4 is all about determining the concentrations of different species in solution, given the fact that we have the Ka. Now, the difference between this and the previous problem we looked at is that we were looking for the Ka value or the Kb value. But now we've got that value and we're actually looking for the concentration of things in solution. So when we're looking at this kind of problem, and I'll just go through the answer here, and then I'll show you the connection to the problems that you'll be solving in the ungraded copy of the practice test, the ungraded copy of the test. We have our solution here. We've got a Ka value, so we know we're getting acid, and you can see the acid there. It's H3O plus in this instance. To be more exacting, this really should have H2O out the front if H2O plus this in order to get the H3O plus. The other way of expressing it would have just been to have H plus here. I didn't take any points off because the spirit of what the student was doing was okay here. So we've got 3.00 molar initially of the acid, and then there's nothing of the products in solution as soon as we start the reaction. But then after a time, what happens is that the compound here begins to dissociate, and it dissociates a certain amount, and that amount is Z. So if we had, I'll just bring up my drawing thing here. Give me a second. I'm going to end up losing the screen sharing for a second, but then it's going to come back.
Okay.
Or maybe I didn't. I can still see you. Oh, that's good. All right. Nice. Okay. Rebecca, you're here twice. That's a neat trick. Okay. So let's say we had this situation here where we've just got AH, AH, and AH. Then after a time, let's say just for kicks, 2 of those dissociate. This is at equilibrium. Then what's happened is that it's split into A minus and H plus. And we know this because We know this because it's Ka, which means that we're getting H plus as a product. And we're also getting something else, the A minus has a product as well. But fortunately, we've got all that listed here as what we need to find. So it's pretty obvious how this is going to pan out, at least as far as what the reactants and products look like. But the point I'm trying to get across is that if two of these split apart, let's say that Z is 2, then we're going to end up getting 2 of these as well, 2 anions and 2 H pluses. And that's why this is set up the way it is. So we end up losing a little bit of the acid, the starting material here, and we gain H plus and this anion in equal amounts, of course, because it splits 1:1. Does anybody have any questions so far?
No, not so far.
So we've got our Ka value or Ka expression here. It's going to be products over reactants. And if we just plug in the equilibrium concentrations, because this is an equilibrium constant, these are equilibrium concentrations, we end up with something like this, Z squared over 3.000 minus Z. And that's just plug and chug. It's just these values put in, Z times Z, which is Z squared, and then this value on the bottom. Now, ordinarily, if you were to try and solve for Z, because that's what we have to do here in order to figure out the concentrations of these different species at equilibrium, we would be forced to use a quadratic equation. And that would be really horrible to have to solve. X equals negative B plus or minus square root B squared minus 4AC all over 2A. Very nasty kind of situation to have to solve. So in order to avoid that, we make an assumption. And that assumption is we assume this is a weak acid. So what we're saying is that the 3.000 minus Z is approximately 3.000. So what does that mean? Well, let me give you an example, a sort of a real life example. Now, as I've gotten older, my eyesight has kind of not been as good as it used to be. So what I've got here, and it's a very bad drawing, it's a drawing of 2 pizzas. I've got a pizza there that's whole, and I've got a pizza there that has less than 5% of the pizza removed. Now, my thing is that because my eyesight's not as good as it used to be, I'm looking at that pizza, and as long as there's less than 5% missing, I see it as a whole pizza. Amazing, isn't it? As long as less than 5% is missing. The same thing occurs with these kinds of compounds. If they dissociate less than 5%, it's almost as if they're not really dissociating at all, which means we can make this assumption, which makes our calculation a whole lot easier. It turns that calculation into 9.50 times 10 to the negative 4 equals Z squared over 3.000, which is a whole lot easier to solve than what we had initially with the 3.000 minus Z. Now you might be saying, well, how do I get away with that? How do I know I can make that assumption when I can't make it? My argument would be as long as this Ka value is small, then that's going to signal the fact that we do have a weak acid in play here, that this will not dissociate very much. By small, I mean anything less than, say, 10 to the negative 4. 10 to the negative 4 or less. Anything higher, it's not really going to be worth trying this because you will probably end up be talking about a strong acid and this won't be as valid anymore. It's probably going to dissociate more than 5% most likely. But there's really 2 things that we're looking at here to see if this is a valid assumption or not. And what we're doing is we take this Z value, which happens to be the concentration of H+, and we divide it into the initial concentration. So part pizza, whole pizza. Think of it that way. Part of the pizza that's been removed and the whole pizza. And as long as that's less than 5%, then we've made a valid assumption. Does anybody have, go on.
I'm sorry, is that an assumption that's kind of an industry standard, or is that just for Chem 2, or?
Oh no, I think it's pretty common. I think a lot of people use it. I think it's arbitrary. It's completely made up. I will admit that. but everybody uses the same sort of made up stuff.
Okay, perfect.
It's kind of like a universal assumption that I guess that a lot of people will make. I don't mind making it, I can tell you that. After you've done that, then you can calculate all of these different species concentration at equilibrium. And it would be Z and Z, which is going to be 0.0534 and 0.0534. The way we get that is we can multiply, we multiply this by 3.00 and take the square root. That will give us the Z value here. And that happens to be the concentration of both of these species. To get the concentration of the acid, it's going to be, I'm going to have to, let me move this over a little bit. There we go. It's going to be 3.0000. This is for the CH3COSH concentration at equilibrium. It's going to be 3.000 minus Z, which is equal to 3.000 minus 0.0534. And if we're going to follow significant figure rules here, then we're going to look at something that has 3 places past the decimal, which is going to be 2.947. And that's how we're going to get that. Now, I know it seems a bit dichotomous, doesn't it? I make this assumption, but then I go ahead, and it's almost like I'm ignoring that assumption now and going ahead and saying, well, you know, this is the concentration of this at the equilibrium. Well, it's still right. It's just less than 5% of what was there anyway. Does anybody have any questions? All right. The next part here, part B, we've got H plus for water is going to be 4.5 times 10 to the negative 7 molar. And we're asking if that concentration of H plus in water needs to be considered in the above calculation. So what's the bottom line here? In solution, there are 2 sources of H plus. One is the acid, CH3COSH, which gives 0.0534 molar H plus. The other is water, which will also dissociate as well. It's associated to H plus and OH minus, but it's producing H plus as well, to the tune of, in this case, we're told it's 4.5 times 10 to the negative 7 molar. Now, that's not very much. So the question is, in this question where we may ask, well, does that 4.5 times 10 to the negative 7 matter? The answer is absolutely not, because let's say we do a little bit of, we'll do a little bit of math here. And if I was to write this out, 0.000045 instead, you can clearly see that by significant figures, this doesn't even change that, and it's just going to be 0.0534. So the bottom line there is that the H plus from the water is so small relative to the H plus that we're actually dealing with, that it doesn't even matter. Your next question, though, is going to be, well, when does it matter then? Well, I would argue it would matter when your acid concentration from the acid you're dealing with is comparable to water, which would mean, I'd say, less than 1 times 10 to the negative 5. Because in that instance, you are now getting into a realm where it could possibly affect the significant figure situation. So as long as your acid concentration is 1 times 10 to the negative 5 or greater, or 1 times 10 to the negative 4 or greater, we'll say, you definitely don't need to worry about the H plus of water. Does anybody have any questions about this?
Nope, you answered the one question I had.
Oh, well, that's good. It's almost like I preempted it. That's cool.
Like you
All
knew.
right. It's like I knew. Psychic. All right. What I'm going to do now is move back here to, let's go back to, what am I doing here? I'm going to go back to the practice test here. And we'll take a look at some of the problems that are on that and how they relate to the problem we just looked at. All right, here we go. So these problems are the calculation of pH and HA from Ka. So this is of similar ilk to what we were just looking at. You can see that we're calculating the concentration of H plus here. And from there, we could possibly get the pH. So in order to get the pH of this, for example, just to show you an example of this, the pH would be fairly simple, negative log of the hydrogen ion concentration. So it would be the negative log of 0.0534. And the pH then would be, I've got my calculator here, so I'll work that out. Would be 1.272. Let's see, is that right? As far as sig figs go, it's going to have, yes, yeah, 1.72. Yeah. It's going to have as many decimal places as it has significant figures. So that has 3 sig figs, which leads to, which leads to 3 decimal places on the log. I don't really want to go into why that is. I do explain it in one of my videos, but that's how we're going to get that. So it's a negative log of that. So how do you get that? You take the log of it, and then you take the minus of that. So when you put log in, it comes out as negative that. And then when you take the negative off that, it becomes 1.272. Any questions about finding the pH of something? Okay. Generally not something people have too much trouble with. Let's go back to this. So what's the pH of a solution of HA that has a Ka of 2.96 times 10 to the negative 5? So what you would do is you'll have your equation here. It'll be HA becomes H plus A minus. And we know it's H plus because it's a Ka that we're given. A is for acid. So there's no real mystery there. So we've got our initial. I'm going to go through the full work of this, even though you probably realistically wouldn't go through this much work, but I'm going to show you exactly how this goes. I think it helps to do it this way. At equilibrium, it's going to be 2.61 minus Z. Let's say Z and Z. And again, we're going to make that assumption that it's a weak acid. And we're able to make that assumption because we do have a small Ka value. It's less than 10 to the negative 3, so we can get away with this assumption, I think, or at least we can try it. Certainly nothing wrong with trying it. And that means that the Ka here is going to be H plus times A minus over HA. And the Ka value we've got there, 2.96 times 10 to the negative 5. And that equals Z squared over 2.61. So you can see that solving for Z is going to be fairly easy. It's just going to be, Z is going to equal the square root of 2.96 times 10 to the negative 5 times 2.61. I'll go ahead and get a figure for that. but it's the same thing as what we would have done on the paper test. And that comes out to be, oops, got to take the square root of that. And I get 0.00879. And Z happens to equal the concentration of H plus. So the pH then would be the negative log of that. And I get 2.056. That's my pH, and that would be my answer. Anybody got any questions? Okay. Now, question 15 deals with the whole.
Actually, Rebecca was
Sorry.
asking that.
I'm sorry.
She has to type in her.
Oh, I'm sorry. Okay. All right. I don't have the chat window up here.
No worries. She's asking, is that the correct sig figs that you just figured there?
I think so. Yeah, because it's three decimal places based on 3 sig figs from over here. Remember, leading zeros aren't significant. Let me see if I can see if I can pull up the chat window, and make it small. I'll keep it. See if I can keep it small. Oh, where are we? Participants. We'll try that. Actually, I don't see your questions in the chat window, Rebecca, which is kind of weird. All right. Okay, I'll rely on you, Donna, to transfer the questions to me if it happens. Thank you. All right. The next question here. Calculate the percentage that allows deliberation of whether or not 1.8 minus H plus is approximately equal to 1.80 accordance with the 5% rule. So what we're looking at here is we want to try and do exactly what we did previously, and then search out that H plus and see if it does actually obey the 5% rule. I tell you what, I'm not going to do it on that specific problem. I'll do it on the one we just did. And in the vein of that same question, close that out. You can see it's 2.61 molar. It turns out the H plus is 0.00879. So the percentage of the H plus to that would equal H plus over AH initial. So H plus at equilibrium times 100%. So in this case, it would be 0.00879 divided by, in this case, 2.61 times 100%. And that would be I get 0.3% or around there. So say about times 10. Here we go. 0.3367% or something like that. We'll say 0.33%, which is certainly less than 5%. So we know that our assumption then was valid. So that's the meaning behind that. And obviously, if you're having trouble figuring out that question, or you should probably look at my solutions, my video solutions, which go through all of this as well. All right. Does anybody have any questions about question 15? Okay. Question 16. It was determined that the H plus was at 0.00396 and the HA was 0.796. What's the new HA? Was correct number of significant figures. Well, it's asking us to do that last step that we did. And again, I think I'll do it based on what I'm seeing here. You're looking for essentially this, which I'm going to circle. That's what we're looking for, 2.61 minus Z. So it'd be 2.61. I'm not doing this question, by the way. I'm doing this, the variant of it, using this over here, minus the 0.00879. And with correct significant figures, I think it'd be 2.60, because you'd only want 2 decimal places in your answer. So I think that's how it would work out. I'll just do a check on that just to make sure that it did take it down by 1, which I think it did. Yeah, it'd be 2.60 was what you'd come out with. And again, that's what it's asking you to do here as well. That one does ask for it with significant figures, so you should abide by that. All right, any questions about 16?
No, we're good.
Okay, 17. So this is that last part that we were talking about, where we were asking whether or not water would need to be taken into account. And in this question, this can vary. So you've got to be on the lookout for that. In this case, though, the H plus is very much higher than the 4.5 times 10 to the negative 7. So the answer is no, it wouldn't need to be taken into account, because when they're added together, it's no, the H plus from the acid is far less than the H. No, that's not right. No, the H plus from the acid is far greater than the H plus from the water. If added together, significant figures from the H plus from the acid are not affected by this. So the answer would be that specific option there. But keep in mind, the answer will vary depending upon how big this is relative to the H2O. If this was less than 1 times 10 to the negative 5, then yeah, I would definitely say, yeah, you're going to have to use a different answer than that.
So is the 4.5 times 10 to the negative 7, is that a standard answer? That's what 5% of H plus coming out of H2O is? It's
kind of like an error thing, because in a standard solution, if you work it out, H plus is going to be 10 to the negative 7. But the maximum it could possibly be might be that plus a little bit more, which is about 4.5 times 10 to the negative 7.
Okay.
The way we get that 10 to the negative 7 is from if you think of the pH scale, it's 14, which is based on 10 to the negative 14, which is the K for water. And then we take the square root of that, that's going to be 10 to the negative 7.
Gotcha.
Which happens to be the pH of neutral water. That's where that comes from. 7. All right. Any other questions about those questions we just looked at, 14 through 17? All right, well, let's look at the buffers. And again, I'll go through, I'll go on. I'm sorry.
It's okay, she just typed it. Would you do any math, i.e. figure, percentage, or just eyeball it for that last question?
Oh, no, eyeball it, because it's going to be obvious either way. It's not going to be ambiguous, I promise. You have my word.
Okay.
Okay. Question 5. In the paper question, the way I handle this is I actually give the pH of the buffer solution before anything gets added to it. But your mission would be to figure out what the pH of the buffer is after a strong acid or strong base has been added to it. All right, so what I'm going to do is just give a very brief going over as to what this is about. But again, this isn't really a substitute. This isn't really a substitute for actually watching the videos about this. All right. Hi, Madonna. I see. It's good to see you. Good to see you here.
Thank you, Doctor. Sorry I'm late because it wouldn't connect in the beginning.
Oh, it's okay. this will be recorded. You'll be able to go back and take a squiz at it later.
Thank you so much.
So initially, the buffer, what is it consisting of? Well, it's a mixture of weak acid and its conjugate base. And the equation for the dissociation is what's really going to matter here. So it'll be AH gives A minus plus H plus. But we have both of these species in the solution. It's going to be a mixture of AH and A minus. So we've got the acid here, and this is the conjugate base, what it turns into. Now the idea is that this has a certain pH. And let's say the pH was, I'm just going to say 4.50. If you add a strong base, so we'll add strong acid first. If you add one equivalent of strong acid to this, what's going to happen is that the A minus will react with the H plus and turn it into AH. The net effect being that the pH isn't going to change much. The pH might go up to, say, well, might go down, say, to 4.40, but certainly not by very much. Now, if I was to add 4 equivalents of H plus, then it would get rid of all the A minus, and then the pH would drop precipitously. We actually do this in the lab, and we do a full demonstration on this in the lab that we're doing this week. So you should take a look at that lab as well for an actual real example of the effectiveness of buffers and how they affect pH. But that's basically what's going to go on there. The other possibility is that we can have this same thing and we can add strong base to it. And strong base in this case would be OH minus. And what would happen is an AH would react with the base. We'd end up with A minus, AH, AH, and A minus, A minus, A minus. And if we did start out off again with a pH of, say, 4.0, this might go up to, say, 4.60. The bottom line is whenever you add acid, the pH is going to go down. Whenever you add base, the pH is going to go up. But if you're adding it to a buffered solution, it's not going to go up or down by very much. Does anybody need any more information than that? As I said, if you want something deeper, you're best off watching the video that goes along with this. Okay. Move this over a little bit here. All right. Now, because we're starting off with a buffer of a certain volume, in this case, it's equal volumes of acid, which is AH, and base, which is A minus, and 200.0 mils of each. We've got a total of 400.0 mils in solution, but then we're going to add to it, in part B, 20.00 mils of, in this case, strong acid, HCl. So it's either going to be HCl or NaOH. HCl is a strong acid, NaOH is a strong base. And you can see what happens is it changes the volume from 400 to 420.0. Now, because of this, we're kind of diluting the solution by changing the volume, which means that we're kind of in a bind here. And what we're going to have to do is not consider concentrations that we're given, but we're going to have to figure out moles of things. The moles aren't really going to change. It's going to be the concentrations that will change when the volume changes. So that's why I have to get this initial moles business going. The initial moles, it's not that hard to get. It's just going to be the concentration of what you're given multiplied by the volume, but it's in liters. And you can see that that's what that 200.0 mils happens to be in liters, 0.2000 liters. Multiply those together, that gives us the moles. Does anybody have any questions so far? To get the moles of A minus, it's the same deal. We take the concentration of the A minus, and again, we multiply it by the volume in liters, and we get that. And we also have the HCl here. We have 20.00 mils of that, and we figure out the number of moles of HCl that we're adding. So those are all initial values that we're getting from the question here. Does anybody have any questions about any of the initial moles? The centerpiece of this question, though, is the next part. What happens when we add the strong acid to the solution? Now, as I said over here, if we take a buffer, which is going to be approximately equal amounts of AH and A minus, we add H plus to it, it's going to react with the A minus and turn that A minus into AH. So the net effect is going to be that we're going to end up adding as many AHs as we would H pluses into the solution. So if 2 H pluses were added, we'd get 2 AHs. So you can see that the AHs are going to go up. That's why it's plus. So the AH is going to go up by the same amount of the moles of HCl that we're adding. So that's why it's 0.0700, which is here, plus this. The A minus, it goes down in concentration. You can see the A minus turns into AH. So that's why that's minus. So that's going to be plus, and that's going to be minus. And that's really the key step in this equation. Does anybody have any questions? The other thing I want you to see or realize is that had this been a strong base, sodium hydroxide, it would have been the opposite. The A minus goes up, as you can see that here, and the AH goes down. So these flip, that becomes minus and that becomes plus. So it matters. It matters what's being added, whether you're adding an acid, a strong acid, or a strong base. Does anybody have any questions about that? Because that's really the centerpiece of this kind of problem. Obviously, we'll have questions like that on the practice test when you see it. After that's been done, you'll have these these moles of AH and A minus, and then you can find their concentrations by dividing by the entire volume in liters, which is given to you 420.0 mils, which is converted to liters. And that comes out as these concentrations. You can see that in the situation we have with the table here, that the concentration of the acid is going to go down a little bit, while the concentration of this conjugate base is going to go up a little bit with this Z here. So this is going to be minus Z, that's going to be plus Z, and Z is also the H plus concentration, which is what we're trying to figure out here to get the pH of this solution. And we do the same thing as we did previously. We assume it's a weak acid. We come up with these concentrations, which are the same as what we started with over here, because these are going to be very small values relative to these here. And we can solve for Z, which happens to be H plus, and then we can get the pH from there. So that's the whole problem in a nutshell, number 5. It's a fairly complicated problem to do all at once, I can tell you that. But the centerpiece of it is this reaction piece, the plus and the minus business here. Does anybody have any questions just about the general problem? Okay. Let's take a look at how this relates then to the practice test. So we're told here, and you can see here what I've done is I've kind of just split this process up into different mini questions based on the original. Okay, a buffer is made up of equal volumes of this AH and A minus, and we're told what the volume is. And then we're told how much NaOH is added here. Now, it could be NaOH, could be HCl. How many moles of AH are present after the addition of sodium hydroxide? All right, so let's see how we manage that. The part of this that we're dealing with is that centerpiece, this part here. That's what we're looking at. So how would we deal with that? Well, what we would do is we'd figure out the moles of, we're only really interested in the moles of AH here. We're not really interested in the moles of A minus actually, because we're being asked here for the moles of AH at the end. So the initial moles of AH is going to be 0.730 mole per liter times 0.343 liters. And that's going to give us a certain amount. I'll go ahead and figure that out. And that's going to be 0.250 moles. We also need the initial moles of OH minus being added. That's from the sodium hydroxide. And that's going to be 0.586 molar times 0.02434. So that's that milliliters there converted into liters. And that would be 0.0142 or 143 moles. So you've got to think about now what effect the OH minus would have on the AH. And the AH would react with the OH minus and turn into A minus and H2O. So we know that what's going to happen is the AH is going to go down. So the final AH here will be the initial AH minus the base. And that would be, especially if we were going to take significant figures into account. I do have a tolerance on these, so it shouldn't be too bad. It should be 0.235 or 0.236 moles. The point is that the amount of AH has gone down because we've added OH minus to it. Does anybody have any questions? The next question is asking about A minus, and it's the addition of HCl. And what happens is that A minus plus H plus here will give AH. So for this one, what you would do is the same thing, except that you would find the initial concentration of A minus and then you subtract the moles of H plus from that. So it would be that would be a subtraction. Did I do a subtraction? Yeah, I did a subtraction as well, but that's on the A minus. This one here, this was an addition, and this one here, this would be addition as well. So what's happening here in question 20 is that you're looking for the moles of A minus, but that's going to go up because we're adding OH minus. It's going to go up by the amount of OH minus we're adding. So we do exactly the same thing as we did over here, except now we add. And likewise here, we're looking for the moles of AH. That one's going to go up as well. All right, does anybody have any questions about those? So that's questions 18 through 20 or 18 through 21. Okay. So which table is going to match? Well, it's going to be the same table as what we've got over here. And you can see that it's going to be the initial concentrations and then minus Z and plus Z and Z over here. So you just choose the one that matches that. The delta is the same as the Z here, and you'll see that in the videos too. So you just match whatever one happens to go there. And question 23, I will go through this one, is the entire thing. It's pretty much exactly what we just did over here, but the whole thing. Now that's a challenging problem right there, right? Because you have to go through and do exactly everything that I just did, depending upon whether it's HCl or NaOH being added, which could be either in this case. So I am going to go through this one. I'll go through it from the beginning, because that is challenging.
Dr. Musgrave, I am
Yes.
so sorry. I need to drop off, but
It's okay.
So I'll watch the video for this last question. Thank you so much.
No worries. No worries. Thanks for coming. Bye-bye. Okay, so we'll start from the beginning here. And what we need is the initial moles. And the way we handle that is we'll look at the AH first, the initial moles for the AH, which is going to be 0.846 moles per liter times the volume, which is 0.439 liters. .371. We have to do the same for the A minus as well, and that's going to be 0.634 times the same volume. And then we're adding HCl, so we're adding H plus, and we'll get the same deal from that. We'll do 0.194 times the amount we're adding in liters, which is 0.01142. And I get 0.00221. Okay, any questions so far about how I'm getting those initial moles of the A minus and the AH? Okay. So here's the reaction moles. This is the most important part of the problem. And we know that the reaction AH is going to be the initial moles of AH, which we just got, plus moles of H plus, and the reaction A minus is going to be the initial moles of A minus minus the moles of H plus. Now understand that these two would flip if it was moles of OH minus that were being added into the buffer. So the reaction moles of AH would be 0.371 moles plus 0.00221 moles. Which would be 0.373 once we took significant figures into account. And then the reaction moles of A minus would be 0.278 minus 0.00221. And let's see, 0.278. and it should be 0.276. Okay. All right, Madonna, you're the only one left here. How are you doing?
I'm doing good. Just a lot to get in at once. I'm trying to understand each part of it.
Okay. Yeah, well, there's a lot to do in this problem. I mean, you have to do the initial moles
Yeah.
first, then you have to do the reaction moles, but you have to understand whether you're going to add or subtract and why you're adding or subtracting. You know, that's really the key.
hmm And actually, I wanted to ask you a question. Last exam, you said that we have to use the calculator in honor log.
Mm.
Is there any way I can use just a basic calculator?
Unfortunately,
Like I can.
no. Let me tell you why,
Um,
Madonna. It's
mhm,
just that the AI for the analog, it
mhm.
flags calculators because they can't tell the difference between a calculator and a cell phone.
Oh,
That's the
the
problem.
thing, yeah. The thing is, I spend so much time trying to make sure I'm doing the calculation right because to be
Mm.
honest, I've never used it before. I'm new to I was a student at SPC, but I haven't been there for maybe like 3 years. So this is my first time back and I've never used Underlog and I don't know what I'm doing wrong, but when I put in the like equation trying to subtract it or divide or doing it with a log last time, I had the answers wrong multiple times
Mm. Well,
and I
you know,
had to keep doing it again.
okay. Well, I've got the link in the syllabus where you can practice
Mm-hmm.
it. Yeah, you can practice
Okay.
using the calculator, and then we can set up a
Okay.
Zoom session to make sure that you're putting in the stuff correctly. And
Yeah, I'm thinking of that.
all
Yes.
right, and you'll know. I mean, the thing is, what I'd recommend is when you're doing this ungraded copy of the practice test,
Mm-hmm.
do it with the on-a-lot calculator because you can bring that up even with the
Oh,
ungraded copy
yeah.
because I've got the link to it. And
Okay.
if you've got the extension already on your browser, you can
Mm-hmm.
easily do a Google search for the on-a-lot calculator and it'll bring it up.
Oh, okay. Okay. That's a great point. Thank you so much. I'll do
But
that because
but
also we get the answers. So I'll
right,
find out whether I'm correct or I'm messing something up.
exactly. And the other thing is you can
Perfect.
always set up a time with me so that we can sort through that if you're not getting the right answers.
Yes, I was planning on doing that as well because of last time, because I spent most of my time trying to figure out the calculator. And
Mm.
to be honest, I got frustrated. I felt like I'm doing the wrong thing. And then I was like, okay, I'm like losing the exam.
Well, yeah, there's a
Um,
lot of calculations in this one, so it's going to be important for you to figure it.
yeah,
Yeah, but
I'm
anyway,
gonna
that's the
go.
issue.
Okay. I'm gonna go ahead and try to practice it.
Hmm.
And then I'll schedule a Zoom with you if I'm still not getting the right answer.
Fair enough.
And yeah, I really appreciate it. Thank you so much, doctor.
Okay, that goes for anybody who's watching this as well. If you need help with this, this is something that I can definitely help with.
Okay.
Okay. Actually, I shouldn't have done that. Let me see. I will have to copy down those results there. If I could ask you to, Madonna, if I could ask you to mute there, you've got some background noise.
Oh, I'm sorry. Sure.
Okay. So we've got AH is equal to 0.373 moles, and the A minus we're getting is 0.276. So I'm just going to get rid of the other stuff on this screen here so that I can continue to do some work with it. So these are reaction moles here. Now the reaction that we're working with is going to be this one. AH gives A minus plus H plus. And we're going to have our little table here, which will be the initial, which is going to be these reaction moles. I should probably say reaction moles here. Now this is before the AH dissociates it all into NEH plus. Oops, actually I've skipped a step here. Sorry about that. We need the concentrations of the AH before we do anything else in the A minus. And the concentration is going to be 0.373 moles divided by the total volume. Now, the total volume is going to be 439.0 times 2 plus the 11.42. And then that's converted into liters. And that would be I'll do it in 2 steps. And it's going to be 0.8894 if we abide by significant figures. That's liters. And I get 0.419 molar on that. And then the A minus, it was 0.276 moles. And again, it's divided by the same amount, which is going to be 0.8894 liters. And that's going to be 0.310 molar. All right, so those are the values that are going to go in this table here. So we'll have the reaction concentrations here, which are going to be, let's see, for the AH, it's 0.419. This is going to be 0.310 for the A minus. And the H plus initially is going to be 0. And then at equilibrium, the AH goes down a little bit. The A minus goes up a little bit. You can use Z or you can use delta or whatever you want. But what we're doing here is we're solving for Z. Now we make the assumption that these are from a weak acid, which is fair enough because it's a buffer, and buffers are by definition made from weak acids. And we now have our values that we can solve with. We've got our Ka is equal to A minus times H plus over AH. And the Ka we're given in the problem, which is 6.95 times 10 to the negative 5. And that's times the A minus, which is 0.310, times the concentration of H plus, divided by 0.419. So we solve for that, and the pH would be the negative log of the H plus, and that'll give you your answer. So I won't go through that last part, but that's how we do it. And again, remember, I have videos for all of these. I have a video for this one too, in the video section. But that was pretty much all I wanted to go through today for this one, and I'll do the other questions on Tuesday. Madonna, do you have anything specific that you wanted to ask?
No, doctor. Thank you so much. I'm gonna go through them, and I'll probably have to schedule like a Zoom with you on Saturday or so. Are you
Okay.
available Saturdays or have to
Yeah,
be
yeah.
weekdays?
Look, I'm available anytime. So just, you know,
Okay.
within a window. So just let me know. Give me by appointment. Just let me know when you want to meet, and we'll meet.
Okay, perfect. I'll do that.
Okay. Thanks,
Thank you
Madonna.
so much, doctor. Have a
All
nice
right.
day.
No worries. I'll see you later.
See you later. Bye bye.